Before airbags, crumple zones, and modern crash testing, safety meant something very different. Some classic cars looked beautiful, but under impact, they revealed serious flaws. And by today's standards, several never would have made it to production. Here are 20 classic cars that under modern safety expectations likely never would have passed. The 1959 Chevrolet Bel Air is often cited as the clearest illustration of progress in crash engineering. In 2009, the Insurance Institute for Highway Safety conducted a controlled, offset crash test between a restored 1959 Bel Air and a modern midsize sedan. The results were stark. Despite its massive steel body and imposing size, the Bel Air's passenger compartment experienced severe structural collapse. The steering column intruded rearward. The dummy recorded catastrophic injury readings. The takeaway wasn't that the Bel Air was defective, it was that it lacked engineered crumple zones. Modern vehicles are designed to absorb impact energy progressively before it reaches occupants. The Bel Air's rigid frame transferred much of that energy directly into the cabin. Under today's offset crash requirements, that structural behavior would not pass. The early Ford Mustang, especially 1964 through 1967 models, revolutionized the market. But safety regulations were minimal at the time. Early Mustangs lacked head restraints, collapsible steering columns in some trims, and meaningful side impact protection. Door beams were minimal. Roof strength standards were non-existent compared to modern requirements. Today, vehicles must protect occupants in side impacts at fixed speeds against rigid barriers. They must limit head injury criteria and chest deflection to strict thresholds. Early Mustangs were never engineered for those scenarios. The Chevrolet Corvair became controversial for its rear-engine handling characteristics, but from a structural standpoint, it also predated advanced crash regulations. Early models lacked dual-circuit braking systems, sophisticated restraint systems, and reinforced side structures. Later government studies suggested the Corvair was not uniquely dangerous compared to competitors. However, by modern crash performance metrics, particularly side intrusion and fuel system integrity, it would require significant redesign. The Volkswagen Beetle, particularly pre-1968 versions, remains beloved worldwide. But early Beetles lacked side impact beams, advanced restraint systems, and modern steering column collapse mechanisms. The short front overhang provided limited crush space in frontal impacts. Modern compact vehicles are engineered with high-strength steel safety cages and carefully tuned crumple zones to compensate for small size. Early Beetles prioritized simplicity and durability, not high-energy crash absorption. Cadillac's full-size models of the early 1960s, such as the Deville, were enormous and luxurious. At the time, weight was often equated with safety. The belief was simple: heavier cars protect better. But crash physics has shown that mass alone does not guarantee survivability. Without engineered deformation zones, heavy structures can transfer enormous forces directly to occupants. Modern vehicles manage crash energy strategically. Early luxury sedans were built rigid, not progressive. Under today's rollover roof strength tests and side pole impact requirements, early Devilles would face major challenges. The 1960s Chevrolet Camaro and Pontiac Firebird prioritized performance and style. Their structural rigidity focused on torsional strength for handling, not controlled deformation during impact. Side door intrusion protection was limited compared to modern standards. Electronic stability control, now mandatory in most countries, did not exist. Loss of control crashes were more common. Modern crash survivability is not just about surviving impact, it's about preventing it in the first place. Compact American cars like the Dodge Dart and Plymouth Valiant reflected cost-conscious engineering during a transitional era in automotive history. They were marketed as practical, affordable, and efficient, and in many ways, they succeeded. But compact design at the time often meant thinner structural components, lighter door construction, and minimal reinforcement in key impact zones. Side impact protection in particular was extremely limited compared to modern standards. Today's vehicles use reinforced steel beams inside doors, high-strength B-pillars, and strategically placed reinforcements designed to absorb lateral forces during T-bone collisions. In contrast, many 1960s compact sedans relied primarily on outer body panels and basic frame structures, which were never engineered to withstand modern side pole or barrier impact simulations. Additionally, modern vehicles must meet strict occupant injury criteria during crash testing. Sensors measure chest compression, head acceleration, femur load, and neck forces. Early compacts were built decades before this level of biomechanical analysis was standard practice. Engineers at the time simply did not have access to the injury data that informs today's safety designs. This doesn't mean they were negligent. It means they were operating within the limits of available research. Full-size pickup trucks from the same era, including early Ford F-Series and Chevrolet C/K models, present another revealing contrast. These trucks were engineered for durability, towing capacity, and rugged use. Frames were strong, suspensions were heavy-duty, but impact energy management was not the priority. Many vintage trucks featured rigid steering columns mounted directly to the frame structure. In a severe frontal collision, that rigidity could translate into dangerous rearward movement toward the driver. Modern vehicles incorporate collapsible steering columns, specifically engineered to compress during impact, reducing injury risk. Dashboards in older trucks were often constructed from painted metal rather than energy-absorbing materials. Today, even interior surfaces are carefully engineered to minimize injury during secondary impacts inside the cabin. Modern pickups must pass not only frontal and side crash standards, but also roof crush tests and electronic stability control mandates. Stability control alone has been credited with significantly reducing rollover incidents, a feature completely absent from mid-century truck design. The AMC Gremlin, though slightly later in peak production, carried over structural philosophies rooted in earlier decades. Its shortened rear end and packaging constraints raised concerns regarding rear impact energy absorption. Today, federal standards require strict post-impact fuel system integrity thresholds to reduce fire risk. Fuel tanks must resist rupture and leakage, even under severe collision conditions. These requirements were developed after years of real-world crash data revealed vulnerabilities in older designs. The Gremlin, like many vehicles of its time, was engineered before these standards became fully developed. The Chevrolet Nova offers another window into the evolution of crash engineering. In controlled modern crash recreations involving similar vintage sedans, one recurring issue is occupant compartment intrusion. When the firewall, dashboard, and steering components move inward during impact, survival space is compromised. Modern vehicles are engineered around the concept of maintaining a rigid passenger safety cell while allowing the front and rear structures to deform. This separation between crush zone and survival space is fundamental to contemporary crash safety philosophy. In many 1960s vehicles, that distinction was far less defined. The Corvette Sting Ray deserves deeper examination as well. Fiberglass body panels contributed to weight reduction and performance gains, but fiberglass does not provide the same structural deformation characteristics as modern high-strength steel safety cages. Today's performance vehicles combine lightweight materials with reinforced occupant cells engineered through computer simulation to manage energy flow during impact. Early Corvettes prioritized agility and styling. Crash energy distribution modeling was not yet part of mainstream automotive development. The original Mini, brilliant in packaging efficiency, presents a unique safety contrast. Its transverse engine layout and front-wheel drive configuration revolutionized small car design. But the vehicle's extremely short front end provided limited distance between occupants and potential impact points. Modern subcompact vehicles overcome similar spatial limitations using carefully engineered front rails and ultra-high-strength steel to control deformation patterns. Advanced airbag systems compensate for reduced cabin space. Early Minis were not designed with those technologies available. The Ford Falcon, structurally similar to early Mustangs, illustrates how mid-century compact sedans approached crash survivability differently. Roof strength standards today require vehicles to withstand loads multiple times their own weight without excessive collapse. This protects occupants during rollover events. In earlier decades, rollover protection was not tested under standardized federal metrics. As a result, many vintage sedans would require reinforced pillars and roof structures to comply with modern criteria. The Mercury Cougar and similar coupes of the era also lacked side curtain airbags, which today deploy to protect occupants' heads during lateral collisions. Modern side pole tests are particularly demanding, simulating high-force impacts against narrow objects like utility poles or trees. These tests measure head injury criteria and thoracic protection levels that early vehicles were never designed to meet. Even Mercedes-Benz, a brand often credited with pioneering safety innovation, demonstrates how far standards have risen. In the 1960s, Mercedes engineers introduced early crumple concepts that were groundbreaking at the time. However, modern crash evaluation now includes multi-angle impact simulations, electronic stability mandates, and pedestrian protection testing, areas that extend far beyond early crumple zone philosophy. The late 1960s Toyota Corolla further highlights global safety evolution. Early global compacts were designed primarily for affordability, fuel efficiency, and mechanical simplicity. Side impact reinforcement was minimal, and advanced restraint systems were limited compared to modern expectations. In today's regulatory environment, even entry-level compact cars must perform well in small overlap frontal testing, side pole impacts, rear crash evaluations, and rollover roof strength assessments. Modern compact vehicles use strategically placed high-strength steel to create a reinforced safety cell around occupants, while allowing designated crush zones to absorb energy away from the cabin. Early Corolla models were engineered long before this survival cell philosophy became universal. While reliable and efficient, their structural design reflected an era when crash survivability metrics were still developing globally, and standardized international testing protocols had not yet been harmonized. The Buick Riviera and Oldsmobile Toronado introduced drivetrain innovation and bold design language. However, their large glass areas and roof structures would face scrutiny under modern roof crush standards. Glass area and pillar thickness are now engineered carefully to balance visibility with structural integrity. The Pontiac GTO illustrates another dimension of safety evolution: crash avoidance and vehicle control. The muscle car era celebrated horsepower, acceleration, and straight-line performance. However, braking technology and stability management systems had not yet evolved at the same pace. Modern vehicles are required to include anti-lock braking systems, electronic stability control, and traction management systems, technologies that significantly reduce the likelihood of loss of control crashes. Electronic stability control alone has been credited with preventing thousands of serious accidents by correcting oversteer or understeer before the driver fully loses control. In contrast, early GTO models relied entirely on driver skill and mechanical grip. Under modern safety regulations, performance vehicles must balance power with advanced braking systems, crash avoidance electronics, and strict stopping distance benchmarks, standards that did not exist during the muscle car era's peak. The Jeep CJ series, designed primarily for rugged off-road capability, presents one of the clearest contrasts with modern SUV safety expectations. Narrow track width, higher center of gravity, and open-top configurations can significantly affect rollover resistance. Today, SUVs must meet strict rollover resistance ratings and pass roof strength tests designed to preserve occupant survival space, even when the vehicle overturns multiple times. Early CJ models were engineered around durability, simplicity, and trail performance, not controlled crash deformation. Side impact protection was minimal, and structural reinforcement in doors and pillars was limited compared to modern SUV architecture. In addition, modern SUVs are required to include electronic stability control systems, which have been proven to dramatically reduce rollover incidents. The CJ was built in an era before electronic crash avoidance technologies were even conceptualized, meaning its design philosophy focused on capability rather than collision mitigation. Finally, the Lincoln Continental of the early 1960s, famous for its rear-hinged suicide doors, represents evolving door retention and side impact standards. While the engineering behind the rear-hinged design was elegant and structurally robust for its time, Modern safety regulations impose extremely strict requirements on door latch strength, hinge integrity, and side impact resistance. Today, doors must remain securely latched under severe crash loads to prevent occupant ejection. Side impact testing includes dynamic pole impacts that place enormous stress on door structures and latch mechanisms. Additionally, modern vehicles incorporate reinforced B-pillars and side curtain airbags to protect occupants' heads during lateral collisions. The Continental was designed decades before these occupant containment systems became mandatory, meaning substantial reinforcement and redesign would be required to satisfy current side impact and ejection mitigation standards. Stepping back, it becomes clear that none of these vehicles were necessarily unsafe in isolation relative to their era. They were built before the establishment of comprehensive federal motor vehicle safety standards in 1966. They were designed before decades of biomechanical research informed injury thresholds. Modern crash test dummies contain dozens of sensors measuring forces across multiple body regions. Engineers now design vehicles using finite element analysis, simulating thousands of crash scenarios digitally before physical prototypes are built. Materials science has evolved dramatically. Ultra-high-strength steel, aluminum alloys, and strategic structural bonding techniques are used to control energy transfer during collisions. Seatbelts incorporate pretensioners and load limiters. Airbags deploy in milliseconds based on crash severity and angle. Electronic stability control systems monitor steering input and wheel speed to prevent loss of control before impact even occurs. Classic vehicles were created before these advancements were standard practice. When enthusiasts say modern cars feel different, they're often correct. The tactile experience, mechanical feedback, and visual identity of vintage cars are unique. But from a crash survivability standpoint, the transformation over the past half-century has been extraordinary. Recognizing that difference does not diminish the legacy of classic cars. It places them within historical context. The automotive world of the 1950s and 1960s valued design freedom, mechanical innovation, and performance. Safety science was still emerging as a discipline informed by data and regulation. Today's vehicles reflect decades of accumulated research, real-world crash data, and regulatory evolution. So when we say that these 20 classic cars might not pass modern safety testing, we are not condemning them. We are acknowledging progress. Engineering evolves, standards rise, knowledge expands. And in the realm of automotive safety, that evolution has fundamentally reshaped what protection means. The classics remain cultural icons. They represent creativity, optimism, and engineering ambition. Modern vehicles represent survivability. Understanding both gives us a fuller appreciation of automotive history, not as a story of failure, but as a story of advancement.